So what I want to do is today I want to talk about some of my favorite problems. But before this, as an Ohio State fan, I was a postdoc there for a year. As a college football fan, I have to talk about the Michigan State game. This is a plot of the probability that Michigan State will win the game as a function of where you are in the game. This is the this is the last play. Michigan is beating Michigan State 23-21. Michigan has the football. It's 4th down. They're around midfield. Essentially, all they have to do is kick the ball to Michigan State and not have Michigan State either run it back for a touchdown or do a Hail Mary pass and defend against the Hail Mary pass. So a lot of sites, ESPN in particular, were saying that the probability that Michigan holds on and wins was 99.8%. Now, the reason I want to talk about this in probability class is not just because it's fun to gloat over another humiliating loss for Michigan, although that is, of course, always, always fun. But I want to talk about how would you actually calculate probabilities of very rare events like this? I'm just curious, how would you calculate the probability of a team winning in a situation like this? What would you do? So one thing is you could try to look at previous data and say how often has this situation arisen before, and then look at how many times the team has actually won in a situation like this. This is the frequentist approach. Another thing is you could try to do mathematical modeling, is you could try to say what is the probability of all the different plays. The danger when you are looking at something that is a very rare event is you may not have enough data points to be very confident about what's going on. And so the difficulty, so the difficulty, we'll have a commercial for Steve Jobs. The difficulty is when you have very unlikely events, and you might have seen this in some of the homework problems. When you're trying to calculate the probabilities of some of these hands, you do not have that many data points. So when the Red Sox came back against the Yankees in 2004, they were down 3-0. This had only happened about 24 times previously in Major League Baseball. It had happened in a few other sports, but you don't have that many data points. So when you're trying to get a sense of exactly how likely or unlikely an event is, you have an enormous challenge with something like this. Yes?
Isn't it also more like also those previous data points also could be unrelated?
They could be unrelated. There could be a reason why you are down 3-0. You could be a worse team. All right, so here is the play. And so Michigan State goes to, okay, I guess we're about to, okay, now the clock is winding down. This is probably, ball is hiked, dropped, picked up, he tries to punt it, tosses to one of, unfortunately, the people on the other team, good blocks, goes in, scores, with time expiring. This was the only moment in the entire game when Michigan State was leading. That's all you need. You just need to be leading when the game is in. Could you raise the screen? But I want you to really think about how you would do a problem like this. We're in a lot of situations where we are very fortunate that we have a nice mathematical theory at our disposal. We can calculate the probability of something happening. In something like this, there are so many different variables going on. How do you really calculate the probability of something like this? What I want to do today is I want to talk about one of my favorite problems. I want to talk about the prize problem. And this is going to be a wonderful springboard to both real-world probability issues as well as a lot of the theory we need to develop. It does fit in nicely with the football stuff we were just doing. And it all comes down to how do you calculate probabilities of events? What are your assumptions in your model? So here's the situation. We have n toy prizes, each equally likely in a box. Each box has exactly one prize. What do you think I might be interested in? How long it takes to get all the prizes. Expected number of boxes to get each prize. Okay? So I have been having some conversations with people at Williams about my non-standard use of props in class. My kids were extremely happy to help out. I said, Daddy needs to go to McDonald's and order a lot of Happy Meals. Are you yes. So I will start showing you the prizes my kids got. I have the Kayla side and the Cam side. So Cameron first got some kind of monster. There are 6 possible prizes. Kayla got motorcycle person. Cam got monster. Kayla got monster. Next one, Kayla got doctor whatever. Cameron got monster. Now, the reason I'm pulling this out is at this point I was fed up. Cameron was being a good sport, but 3 monsters in 3 tries, 4 monsters out of 6 was a bit too much. So we went to the manager of McDonald's and asked, we have more than enough data for the probability class at this point. Can we please give my son something other than a monster? And he said, sure. Are you surprised? 4 monsters in 6. How does this compare to Michigan State? It's not nearly as satisfying to me, especially since, Kim was like, can I get something other than... I mean, they did make up a really nice story about the identical twins who then became triplets and then quadruplets, but how would you calculate the probability of an event like this? So in statistics, you'll start testing hypotheses. What might be your initial hypothesis? All equally likely. So we want to figure out what is the right event to calculate. Do we want to calculate the probability of getting exactly 4 of these monsters? Is that the event we should be looking at? Or should we be looking at a slightly different but related event? What different event should we be looking at? There's 2 ways we need to generalize this. It's not just looking at the probability of getting exactly 4 of this monster. This goes back in 2000 when Clinton and Obama tied in Syracuse, New York. If I tell you ahead of time that they're going to tie in Syracuse, New York, that means something. If I don't specify ahead of time where they're going to tie, it's a very different problem. It's much more likely that they'll tie somewhere. I really don't want to know what's the probability I get 4 of these monsters. What do I want to know? The probability that I get 4 of one of them. I don't care ahead of time which one it is. It turned out to be monster, but maybe it could have been motorcycle. I actually don't even want to calculate the probability that I get 4 of one thing. I want to calculate the probability that I get at least 4. If I get 4 of them, or 5 of them, or 6 of them, to me that would be a very unlikely event. So what would that probability be? So probability at least 4 of the 6 are the same. So this is a nice way to review some of our probability. So what would the answer be? How would we calculate this probability? There will be 6 prizes. So it's a little bit annoying that they're the same. So 6 prizes. And we'll assume all equally likely. So how many choices do we have for the one we get 4 times? 6 choose 4. Not 6 choose 4. 6 choose 1. We have 6 prizes. We choose one of the prize to be the one we'll get at least 4 times. And now we're going to do a sum. N goes from 4 to 6. And we're going to look at how many ways we could get exactly 4 of the same prize, exactly 5 of the same prize, exactly 6 of the same prize. So N will be the number of times I get that repeated one. What's the probability I get that specific prize? It's 1/6. And I raise that to the nth power. And then the other 2 prizes can be any of the remaining 5. So what's the probability for each of those? 5/6. And how many of those do I have? 6 minus n. So if you do the calculation, now I got to move some of these things, you get 5.22%. If I don't include this 6 here, if I actually specified the monster ahead of time, I would divide by 6 and I would have something less than 1%. What do you think? 5.22%. Is this shocking? I think we all agree that it's unlikely. But if you do a lot of different social sciences, they often have different thresholds. You know, is it within 1%? Is it within 5%? These numbers are somewhat arbitrary. What do you think? Would you be surprised at something happening that only has a 5% likelihood? No one's surprised?
Well, I mean, how many times do you go to McDonald's in a year?
Not that often. And I will admit, bless you, I came very close to driving to yet another McDonald's to just see if we would get even more of the monsters. I was curious, and my kids were gung-ho. They were really encouraging this, and I said, no, there's a limit to how many times I will go to McDonald's. I'm not going to McDonald's again. But it was close. It was very, very close. I'd love more data points. You would love to be able to do that. Michigan and Michigan State are not going to play 6 more football games in the next week to give us more data points for something like this. 5% to me is not extremely likely, but it's not so unlikely that I disbelieve this and I think something has gone wrong. If you tell me, you know, my kids and I played 6 hands of bridge, and in 4 of those hands, somebody was dealt all cards in one suit, I'd be shocked. Here at 5%, I'm a little bit amused, but it's not so overwhelming. So if you continue in statistics, you'll do a lot more with hypothesis testing. This is one of the great applications of probability. And I wanted to emphasize how you try to calculate something like this. You've got to be very careful to answer the right question, to gather the right data, to set up the right computation. I want to know how likely is it that I'm getting at least 4 of the same toy, not exactly 4 of this particular monster. This one is Joe, and I think this one is Bill. Okay, so any questions about this calculation? This is related to the prize problem in a very obvious way. The only difference is rather than being in a box, it's in a Happy Meal. Do you think the 6 prizes are all equally likely to appear in the McDonald's box? No, and in fact, when I said, please, can my son have something other than another monster? The manager said, geez, the only toy I have left is Motorcycle Person. Do we think all the toys would be equally likely? No, the goal is to get people to come. You want people to try to collect the whole set. And so there's a real incentive. The question is, what is the optimal distribution of probabilities? For simplicity, we will assume all the toys are equally likely in a box. This makes the problem a lot easier to study. It's not necessarily a real defensible hypothesis. Okay? Now what I want to do is, before we go into detail, we're going to need to understand a geometric random variable. So I want to first review geometric random variables. Geometric random variable. So we say x is a geometric random variable with parameter p if the following is true. The probability that x equals n is 1 minus p to the n minus 1 times p if n is in the set 1, 2, 3, the positive integers. Unfortunately, depending on which book you use, there could be slightly different definitions of what is a geometric random variable. Same thing with what's the definition of an exponential random variable. You can change a little bit. I'm going to view p as the probability of success. You could view p as the probability of failure. So there's a way to interpret this. So there's a nice interpretation. If p is probability of success, this is the probability first success on the nth toss of a coin that is a success with probability p, and all tosses are independent. So if possible, you always want to tell a story. And so imagine I have a coin that has a probability p of landing on a head. I'll call heads a success. So I keep tossing the coin until I get my first head, and then we stop. What's the probability my first head is on the nth toss? Well, I have n tosses. What must the final toss be? Must be a head. If my first head is on the nth toss, what must the first n minus 1 tosses be? Tails. So if I want my first head to be on toss n, it would be 1 minus p to the n minus 1. The first n minus 1 are all failures, and then I have a success. You can generalize this to what's called the negative binomial distribution, where you can say, I want to calculate the probability my fifth success is on the nth toss. These are very useful distributions to look at. Yes?
Is that at sign from? Like,
Over here?
yeah.
That's with probability. Oh, this with probability. Sorry, I wrote the wrong one. With probability p. So we have a nice interpretation for what this is. We keep tossing a coin, and then we stop once we finally get a head, and we want to know how long do we wait. And once we have a head, it's a success. Hopefully you can begin to see why this might be related to the toy problem. Is I'm going to be opening, and now what I'm going to do is a specific toy might be my success. We're going to see a lot of really good mathematics. Whenever you see a random variable, the very first thing you should ask yourself is, what does its mean? What is the expected value? What's the next question you should ask after the mean? Variance or the standard deviation, right? Either one is a fine second question. So what is the expected value of x? All right, well, unfortunately, this is going to involve a sum. Sums are going to be difficult. So we want to do the following. The expected value of x, and it's going to be the sum, n goes from 1 to infinity, the probability x equals n times n. Well, actually, I think normally we write the n first. So n times the probability. And this is going to be the sum, n goes from 1 to infinity, of n times 1 minus p to the n minus 1 times p. Okay? Because I know where things are going, I'm going to modify things just a little bit. I'm going to pull out the p, and I'm going to have it, the sum goes from n goes from 0 to infinity of n times 1 minus p to the n minus 1. I can't pull the n outside, of course, because the sum involves n, but I can pull the p out. I've also extended the sum going all the way down to 0. Am I allowed to extend the sum to 0? Yeah. Because when I put in n equals 0, I just have a 0 here. So we need to evaluate this sum. This sum is extremely close to something you know how to do. What is preventing this from being something you know? The n. So let's just remove the n, and can we evaluate it? Yes. Now, unfortunately, we can't just remove the n. So this leads to one of my favorite methods in mathematics. It's called the method of differentiating identities. So the whole point of differentiating identities is you start with something you know. And the whole point is you take an identity and you create infinitely many new identities from the identity you already have. If you think about it, it takes a lot of work to prove an equality. It takes a lot of work to prove an identity. It's a shame once you have this to just set it aside. You want to milk it and you want to get other things from it. So the idea is, can we somehow create additional equalities from the geometric series formula? So we spent a lot of time, I think first day of class, if not second day of class, the basketball problem, talking about the geometric sum. And we found a closed form expression for that sum. And now what we want to do is we want to now use that here. And so we want to somehow tweak this and use that to get new expressions. All right, so now we know, bless you, the sum, n goes from 0 to infinity of x to the n equals what? So what does this equal? I'm sorry, what is it? Well, I'm going from 0 to infinity. 1 over 1 minus x, so long as the absolute value of x is less than 1. So we have the infinite geometric series formula. We want to make sure x is less than 1. That's not going to be a problem for us. What we want to do is we want to somehow relate this to this expression. So if you look, what do you think we want x to be at the end of the day? Probably x is going to become 1 minus p. How can we go from something like x to the n to n 1 minus p or nx to the n minus 1? What's the suggestion we do? Take the derivative. Can I say the derivative of a sum is the sum of the derivatives? If it's finite, yes. This is unfortunately infinite. So you need to justify interchanging the sum and the derivative. It turns out you can do it, and if people are interested, I'll show you some places to read to justify this. One thing that saves us is the tail of a geometric series is a geometric series. So I'm only going to just write down this for one moment, and then I'm going to immediately erase it. N goes from 0 to n of x to the n, plus the sum, we'll do n minus 1 maybe, n goes from n to infinity of x to the n. Well, this piece here, I can pull out an x to the n, and then I have a sum, n goes from big N, from 0 to infinity of x to the n. I just pull it out and I re-index. And then this is a geometric series. And so I now get x to the n over 1 minus x. And I can actually replace this infinite sum with a finite sum up to n minus 1 and then one extra term. Now that I only have a finite number of terms, I can now differentiate, and then I can take the limit as big N goes to infinity. And so if I do all this, I will be fine. The geometric series is extremely special in this regards. In most cases, you are not going to be lucky enough to be able to do this. Fortunately, this is the most important example. And we can use the fact that the geometric series, the tail of a geometric series, is a geometric series. All right. That said, this is a lecture about toys at McDonald's. I feel very immature and childish right now, so I have no problem not worrying about all these technical obstructions. Let's just say the derivative of a sum is the sum of the derivative and move on. So now we would get, so we're going to apply d by dx. And then we'll get a sum, n goes from 0 to infinity of n x to the n minus 1. And when we apply the derivative here, we have 1 minus x to the negative 1. The negative 1 comes down, 1 minus x to the negative 2. We take the derivative of the inside, we get another negative sign, and we get 1 over 1 minus x squared when the dust settles. And so now, if we take x equals 1 minus p, this implies the sum, n goes from 0 to infinity of n 1 minus p to the n minus 1 is 1 over 1 minus p squared, which is 1 over p squared. So we have a formula for the infinite sum we need. And now we can feed that in, and then we get that the expected value of x is just going to be p times 1 over p squared, which is 1 over p. So we now have the expected value of a geometric random variable. There's a couple of points I want to really hop on. The first is, whenever you calculate something, you should always ask, is this answer reasonable? What can you tell me about the expected value of a geometric random variable? What information do you know about it before you do any calculations? I want to know, on average, how many boxes do I need to open before I have a success? I want to know how many tosses of the coin do I have to do before I get my first head? Do we know anything about the answer?
At least one.
At least one. I don't care how lucky you are. You must toss the coin to get a success. Okay? There's a really good joke about somebody wanting to win the lottery. I'll try to remember to share that. You've got to play. You can't have a success earlier than 1. So whatever our answer is, it's got to be at least as large as 1. Do you think it's exactly 1, or do you think it's greater than 1? What's the only way it could be exactly 1? Yes, if you use the Mobius coin, which always lands on a head. You toss the coin that's always a head, it'll take you one toss, the expected value is 1. We know that extreme case. Always look at extreme cases. If p equals 1, the expected value is 1. Excellent. Because p is less than 1, 1 over p is greater than 1. So it's going to take us more than one toss in overall. So this passes the smell test. And you really want to do this every time you do a calculation. You want to ask, is this reasonable? Are there some special cases you can check? Have you made an algebra mistake? My algebra is atrocious. It's quite likely I've made a mistake somewhere, but at least this passes the basic tests I can think of. The next thing, which is a little bit harder to decide, is do we really want to do x, taking derivatives with respect to x? Or we might want to do something a little bit different. So because we had something of the form 1 minus p to the n minus 1, it made it very natural to take the derivative with respect to x. If instead we had 1 minus p to the n, we might want to take the derivative with respect to x and then multiply by x. So if you have a slightly different algebraic expression, we'll talk more about this later, it might be more convenient to look at the operator x d by dx, take the derivative with respect to x, and then multiply back upwards. It all depends on the algebra you're trying to do. And we'll see other examples later. Okay, any questions on what we've done so far? So this is the geometric random variable. It's one of the more important of the different random variables. It's going to be crucial in understanding the prize problem. We've seen now differentiating identities, which is one of the main techniques to calculating moments, to calculate means, variances, standard deviations. All right, now what we want to do is we want to apply this. There's one last technique that we need to use, and it's something we proved in Wednesday's class. Now, it always feels like a long vacation with Mountain Day and whatnot. Does anybody have any rough idea of what was the big result we proved at the end of class on Wednesday? Without looking at notes. Yeah. Well, at least if you're going to do it so that I don't hear the paper ruffling. What was the big thing we proved? The expected value of a sum is the sum of the expected values. So linearity of expectation is one of the most powerful techniques we have. There's many reasons I love this problem. It allows us to introduce one of the standard random variables in a very natural setting. It gives us an excuse to talk about differentiating identities, one of our most useful techniques. It allows us to talk about expected value of a sum is the sum of expected values, linearity of expectation, one of the most important properties of the linearity operator. It also gives me a chance to do some data analysis on McDonald's and talk about when do you think an unlikely event is happening. It was entirely coincidental that Michigan State came through and Michigan choked and gave a really good sports example to link this to. But you really want to get a sense of unlikely events. So we want to know how many boxes we need. Well, I've already told you, you should do a smell test. Do you want to try to get the smell test? Do you want to try to get your guesses before or after you do the calculation? Before or after? Before. If you do the calculation, you are going to be influenced by what you see. You always want to write down what you think the answer is before you start doing the calculation and start getting these blinders on. I'll send a great story by Isaac Asimov on The Planet That Wasn't, where scientists were actually blinded by their preconceptions and misinterpreted data because they had a feeling that this is what the answer was, and they looked at things in such a ways to get that to happen. Can anybody give me a lower bound for number of boxes? N, thank you. And you could have given me a worse lower bound. I'm grateful nobody gave me 0 as a lower bound. So number of boxes has to be greater than or equal to n. There's n prizes. There's 1 box per prize. I'm sorry, 1 prize per box. We clearly need at least n. Is there any finite upper bound that's guaranteed to work? No. There's no finite upper bound. But what do you think would be a reasonable upper bound? Upper bound for expected number. Any thoughts on what would be a reasonable upper bound?
The number of toys that exist. So like millions or something.
Oh, in the whole world? There are actually infinitely many toys. You know how McDonald's has served billions and billions? That's only on Terra. It's actually an intergalactic empire. Sorry. There's infinitely many toys. It could go on forever. Any reasonable upper bounds? Why n factorial? Just because it's big?
toys in like the first n boxes.
Okay.
And then we're only looking for like n-1 other toys.
Okay.
And we get like
Okay, so one idea, so you could actually justify n factorial by some kind of recursive argument. And let's say we prove this by induction up to, say, 5 toys. Then for the 6 toys, let's say it's going to take us 6 boxes to get that first toy. And now we have 5 boxes, which by induction is 5 factorial. So you could do n factorial. You can actually do a lot better than n factorial as a reasonable upper bound.
n squared.
You could do n squared. You could even do a little bit better than n squared, but essentially each toy is going to take you about n boxes. So maybe the first set of n boxes gives me my first toy, the second set gives me my second toy. I expect a number somewhere between n and n squared.
Would you do n times n-1 over 2?
I might do like n plus n minus 1 plus n minus 2, something like that. But I don't really want to worry about constants so much. I want to just say on the order, how does this grow with n? I want to see how does the problem scale. And that's a big issue in a lot of this. You want to figure out how does things scale. If I triple n, how do I expect the weight to go? What do you think you should be doing right now if you were at home? You should be coding. You should write a code to calculate this and see how long it takes. And we've talked about different tricks to do this. We could call the prizes 1, 2, 3, 4, 5. What's a better label for the prizes? 1, 10, 100. So code. And the prizes are 1, 10, 100, 1,000. And then if we have n prizes, you just compare to the sum. K goes from 0 to n minus 1, 10 to the k. Now we've got to be a little bit careful. Yes?
I was going to say, doesn't it just tell you if you have exactly one of each?
Right. And so you've got to be a little bit careful. It's not quite the same as this. So what you could do is, ideally you would love to do something like this and just make sure that you have something non-zero in each of these digits.
But then can you get 10 of prize 1?
You could get 10 of prize 1. And so what you need to do in some sense is really shift to counter variables. This is a nice thing to try, but you're absolutely right. You're beating me to the punch. This is going to have issues. If I have multiple copies of one thing, I can't keep getting more and more credit. Now what's nice here is that we are getting the numbers one at a time. I'm not randomly generating a whole stream. So what we would probably want to do, is that's sadly not going to work, is we have prizes of k will initially be empty. And every time we get a prize, we increase the counter. Yes?
Could we also use prime numbers?
I was about to say you could use prime numbers. And then this is similar to what we've been doing there. Is if we use prime numbers, you can then just check the remainders. So the prizes could also be 2, 3, 5, 7, 11, and look at remainder. Now, unfortunately, if you try doing the primes like this, if it takes a large number of boxes, you have a huge number that you're now taking remainders of. So from a coding perspective, this could become challenging. So I don't want to get into too much of the coding right now. I encourage you to go home, try the different ways, see which ways work, and see if they work fast. And if they don't work fast, try to think of other ways. So we're going to now try to figure out the expected number of boxes we need. What happens on the very first box we open?
You get a prize.
We get a prize. Is it a prize we have or don't have? Yes, I mean, when we were doing this in real life, the kids were initially happy they got different. And then because I had some feeling how McDonald's works, and I don't mind if they hear this, I actually tried to have my kids agree ahead of time. If they happen to get a prize that they already have, but their sibling does not have, will they automatically agree to exchange prizes? When they both ended up getting this, it did not matter. So the first box you open is good. What about the next box you open? What do you think? Good or not good? 5/6 probability. So what we're going to do is we're going to introduce the random variable. So xk is going to be how long you wait to get the kth distinct toy given you have k minus 1 distinct toys already. So what do we know about x1? 1. It's x1 is always 1 with probability 1. Because we have no toys. So whatever we get is a new toy, we're happy. What about xk? What kind of random variable do you think xk is? Probably a geometric random variable, given the fact that we've started this with a lecture on geometric random variables. So if it's a geometric random variable, you have to tell me which geometric random variable. What's the probability of success? So xk is geometric, and what's the probability of success? What's the probability we get a prize we don't already have? So it's n minus 1 over n if we're doing x2. But I want to do xk, the more general. So we'll do x2 first. It's going to be n minus 1 over n. We have n possible prizes. We already have 1, so the probability we get something new is going to be n minus 1 over n. If we wanted to calculate x3, we would already have 2 distinct prizes, so it would become n minus 2. So the general case, if I have xk, it would be geometric, and what would be the probability of success? N minus k minus 1 over n. I'm going to just keep the k minus 1 in parentheses to just remind myself where this is coming from. I have k minus 1 prizes. I need to choose one of the other prizes. There's n minus k minus 1 that work out of n. So now we have a nice series of random variables. And we know how long we have to wait. We know the expected value of a geometric random variable. So we let x be x1 plus xn. Do we go all the way up to xn? This is how long we have to wait for the first prize, given that we have none. Then once we have the first prize, then we have to wait until we get the second distinct prize, that's x2. And then all the way we have to wait till we get the nth distinct prize. So this random variable will tell us how long we need to wait. And we've broken this complicated process into a bunch of simpler ones, a bunch of geometric random variables. This is what you want to do. You want to reduce to simple cases that you already know. And now we can use the linearity of expectation. The expected value of x is going to be the expected value of x1 plus the expected value of xn. What's the expected value of x1? 1. What's the expected value of x2? N over n minus 1. All right, if it's n over n minus 1, do I really want to write the expected value of x1 as 1? How do I want to write it? As n over n. Algebra matters. The next one will be n over n minus 2, all the way down to the very last one, which is n over n minus 1. Sorry, n over 1. Let's think about this. Does this make sense? In the beginning, I'm getting new prizes very fast. Basically, I need to open just another box and I get a new prize that I haven't seen before. Towards the end, it's taking me a long time to get a new prize on the order of the number of possible prizes. That makes sense. You know, to get that final last prize, you would expect to take a long time. All right, so if you look at this, what algebraic things can you notice? We can pull out an n. And then if I write them in the other order, if I start from here and go down, this is equal to n times 1 plus 1/2 plus 1/3 plus 1 over n. Have you seen this sum? What's
Sorry, I don't, how did you do it?
okay? So I pull out an n, and I've got 1 over n plus 1 over n minus 1 plus 1 over n minus 2 all the way to plus 1 over 1. And I'm now just writing it in reverse order. And by writing it in reverse order, this hopefully looks like something we've seen before. So what is this? It's about the harmonic series. And the harmonic series is about log n, if you sum the first n terms. So this should be approximately n log n. And again, we use log to represent log base e. We could do a little bit better. There's really good approximations for the sum of the harmonic series. But this gives us a really good testable prediction that we can now do our computer code. Does this pass all of our smell tests? Yeah. It's greater than n. It's less than n squared. It's a lot closer to n than n squared. That makes sense because in the beginning, we're going to be getting a lot of prizes, a lot of distinct prizes fairly quickly. So having to go all the way up to n squared, that seems like being overly pessimistic. Does anybody remember how you prove that this is approximately the log of n? Not Taylor series, no. How do we show that the sum of 1 plus 1/2 plus 1/3? It's something from one of your old calc classes. It's been a while. Yes? All right, so since nobody is remembering, nobody remembers? Nope. Nope. So we want to study the sum, n goes from 1 to n of 1 over n. This is approximately equal to, we don't like sums. What do we like? Integrals. So this is approximately the integral from 1 to n of 1 over t dt. This is the integral test. And then if you want to do this properly, you can figure out, do I want to go from 1 to n, from 1 to n plus 1, stuff like that. Let's just do it very quick and easy like this. And if we go from 1 to n, this is going to be the natural log of n minus the natural log of 1. Well, that's just the natural log of n. And then because the function is monotonic, the function is strictly decreasing, the amount of error I have is at most the first term, which means it's at most 1. So I'm off by at most 1 from this. So the log of n is actually very accurate. We can refine this. We can do better versions of integral test. But this is how we can finish the problem. So there is an enormous wealth of material in this one example. Okay, estimating probabilities of unlikely events, seeing the power of linearity of expectation, seeing the power of known random variables, building complicated random variables out of simple random variables, using differentiating identities to get a handle on the mean. Now, this just gives us the average wait time. Do you want to know more than just the average wait time? We know on average how many boxes we need. What might you like to know as well? So related to the probability, we might have to wait a lot longer. How much it varies? The variance. The simplest way of measuring how long must we wait above and below this. How likely are we that it will happen in a lot less than n log n? N log n is not that bad compared to n. Log n goes to infinity, but slowly. N log n, for all practical purposes, it's n. But maybe this is just the expected value. Maybe every now and then it's really bad and waiting for those final few is painful. So the question might be, can you give me a 90% confidence window where 90% of the time, if all the prizes are equally likely, I will wait between this many, I'll need this many boxes to this many boxes. So you'll do a lot of this in a statistics class. This is where the probability we're developing comes into play. This class is co-listed. I do recognize that this is supposed to also be a statistics course, which is why even though we are concentrating more on the theory, I want you to get a sense of why we care about the theory. It's not just for pure mathematics. This is going to allow us to build good statistical tests later on. And we really want to know how long we're going to have to wait. Now, unfortunately, to calculate the variance, we need to deal with the expected value of x squared. Calculating the expected value of squares of quantities is significantly harder than calculating the expected value of sums of quantities. And the reason is the squaring function is not linear. The expected value of a sum of squares is not always the sum of the squares, especially if there are dependencies. And so the expected value of a sum is the sum of the expected values. That works irregardless of whether or not things are independent or not. If there's dependencies, it doesn't matter. The expected value of a sum is still the sum of the expected values. If we have dependencies, it's a different story. All right, so we've got about 5 minutes left. What I want to do for the remaining 5 minutes is talk a little bit about how you would calculate some of the other quantities. So we'll stay with the geometric random variable. That's a good one to look at. And then we'll do a lot more with differentiating identities, normalizing constants, special probability distributions on Wednesday. So more on differentiating. Okay. So we've already calculated the expected value of x. The expected value of x squared is going to be the sum, and goes from 1 to infinity, of n squared probability x equals n. The variance of x, there's two ways of calculating it. It's the expected value of x minus the mean squared, or if you do some algebra, and the algebra is done in the book, it's the expected value of x squared minus the square of the expected value of x. If you look at this, in some sense, the variance measures the lack of commutativity between the two operations. I square x, and then I take the expected value, or I take the expected value, and then I square it. Which do you think is typically going to have greater cancellation? Taking the expected value and then squaring, or squaring and then taking the expected value? Would you expect more cancellation? The second. Because here I can have positive and negative things canceling out. Here I'm squaring, so there's no chance of cancellation. It turns out this quantity is always greater than or equal to 0. If you look at just this expression over here, it is not clear that this expression is always non-negative. But if you look at this expression over here, where mu is the expected value of x, now it is clear. Because in this case, I am taking the expected value of a quantity squared. That can't be negative. So for the geometric variable, the expected value of x squared is going to be the sum, n goes from 0 to infinity, of n squared. The probability x equals n is 1 minus p to the n minus 1 times p. I can write this. I can pull a few things out. I can write this as p over 1 minus p times the sum, n goes from 0 to infinity, of n squared 1 minus p to the n. The reason I'm doing this is I don't like the fact that I have an n squared and a 1 minus p to the n minus 1. The question is always, what is the best way to do the algebra? We have an n squared. If I have an n squared, I want to differentiate twice to get an n squared to come down. But if I differentiate x to the n twice, I'm going to get n x to the n minus 1, and then I'll get n times n minus 1 x to the n minus 2. I don't want to have n times n minus 1. I could fix this by inclusion-exclusion, by adding and subtracting things back. Or what I can do is I'm going to apply the operator x d by dx twice. And if we apply this operator twice, we're going to keep the power of x to the n each time. And then the derivatives are going to become a little bit easier. So again, it doesn't matter which way you do the algebra, except in terms of how much of your life you want to spend doing algebra. So if we start off with the sum, n goes from 0 to infinity of x to the n is 1 minus x to the negative 1. Let's apply x d by dx once. If we apply x d by dx once, we get the sum, n goes from 0 to infinity of x times n x to the n minus 1 equals x times 1 minus x to the negative 2. I first differentiate and I pull the derivative inside, and then I multiply by x. Well, what should I do with this x? Bring it inside. And so I bring that x inside, and I have n x to the n. And now if I take the derivative again and multiply by x, I'll have n squared x to the n. So now I do it again, apply x d by dx, and we'll be left with the sum, n goes from 0 to infinity, of n squared x to the n is now x times d by dx, and x 1 minus x to the negative 2. If I have done everything correctly, it is now time to stop class, which means I do not have to do the rest of this algebra. It is just now standard algebra and calculus. Right? You now take the derivative, you use either the quotient rule or the product rule, then you multiply by x, and there's your formula. And from this point, you can now simplify and now deduce all that you want. Okay.